Okay, thank you. So this is a joint work with two colleagues, Nick and Gardner from the US Los Alamos Laboratory and Eric Matzner from Rennes University. Here we are interested in rare event estimation for a fixed probability distribution, not for a random process. And namely, X denotes a d-dimensional random vector with low mu that we can simulate. And phi is a mapping from RD to R, and we'll call it the score function. Okay, and this function acts as a black box. That means give an x, it will give you phi of x, but you don't have any further information about phi, no closed form formula, no analytical expression, etc. Okay. Then y is equal to phi of x is just a random variable on the real line, and you want to estimate the probability p that this random variable y is larger than q, given that this probability is very, very small. Okay, for example, 10 to the minus 12. So two remarks are in order. First, we all know here that in this context, classical Monte Carlo is intractable because you would need to make at least about 1 trillion experiments to see your rare event happen, and you can even derive an exact formula for the variance of your estimator, and we will compare our method with this one just to give an idea. The second remark, more important, is that phi is a black box. In fact, you don't have any idea of how you could twist the law of x just to make some large values of y appear. So we exclude important sampling also. So the other big families of techniques for dealing with rare event is multi-level splitting, and our new method belongs to this family. So first of all, I give an example. The motivation from this work comes from problems in digital watermarking. So roughly speaking, digital watermarking is a set of techniques for embedding information in digital documents such as audio files, images, video files, etc. Ideally, this the watermark must be both invisible. That means if it's some music, you can hear it. If it's an image, you can see it. Or if it's video, it must be robust to corruption because there could be noise in the channels, etc. And most of all, it must be hard to remove. So, for example, you buy a DVD with copyright protection, and you would like to copy it, but you are not allowed. In the system, there is a detection, and this detection computes a score, phi of x, and if this score is above a certain threshold q, then you are not allowed to copy it. Okay, but that was the big picture for watermarking. But here we are not interested in designing watermarking techniques. We just are interested in evaluating false detection probabilities. So what is a false detection? For example, you have your own document, which of course is not watermarked, and you want to copy it for your own use, for your friends. But there is a problem because the detector considers it as watermarked, and so you can't copy it. So recently, standard groups for DVD copyright protection decided that this probability of false detection should be less than 10 to the minus 12. And as you can see, since this detection is based on the score function, we are exactly in the framework of the general framework of the previous slide. Okay, now let us focus our attention on a very precise example of watermarking, which was proposed in the late 90s. I insist on the fact that it's a very simple technique, but we can illustrate our algorithm and benchmark our method on this. Okay, so how does it work? When you have an image, the detector extracts a few wavelet coefficients from this image, and then computes the normalized correlations of this vector, the vector made of these wavelet coefficients. It computes these scores and then compares it to a threshold. If the score is above the threshold, then your document is considered as watermark. Okay, U is a secret vector. which makes the watermark hard to remove, of course. But in our problem, we want to estimate a false detection, and when x is not watermarked, a common assumption is that this vector x, in fact, is just radially symmetric distribution. Okay, it's isotropic, and since only the normalized version of x appears here, it means that you can take any isotropic distribution for x, it will make the job. So in the following, we will consider that x as a Gaussian standard distribution. So now here is a problem. Considers d equal to 20, q equal to 0.95, u to be the first vector of the canonical basis, and we want to compute the probability that phi of x is above q when x has a standard distribution. So I said that our algorithm is a multi-level splitting algorithm, and it works in several steps. The first step is, for the first step, just makes the same thing as with classical Monte Carlo. That means on the left-hand side of the slide, you just draw n IID points according to the law of x, which is just a Gaussian distribution. On the right-hand side, we have computed the scores of these points. Okay, on both sides, you have in red the rare event. So we want to compute this probability. Okay. So at the first step, once you have your endpoints, you compute their scores, and you denote L1 the minimal score. So it's the red cross. It's reach for the red cross here. Then you kill this point and you replace it by a new point, which is distributed according to the law of x, knowing that its score is greater than L1. Okay, so I will explain later how we can do it, at least approximately, but for now and for the theoretical study, we will consider that we can do it perfectly. Okay, that's the assumption. So we do that, and then once we have our new point in blue and the new point here, we have again a sample of n IID points distributed according to the law of x, knowing that the score is greater than L1, and we do exactly the same thing. That means we are looking for the new minimal score. We kill the particles, we replace it by a particle which is well placed, and we iterate this reasoning. Until when? Until we have managed to put all the points in the rare event region. Okay? And that happens and when there are two intermediate q, the quantile of interest is between two intermediate levels. Okay? Then what is our estimator? Of course, what is random here is capital M. The number of steps before you manage to put all the crosses in the rare event region. Then what do you say? You say that the probability of the rare event is approximately the probability of being above Lm, but the probability of being above Lm by base formula is the probability of being above L1, and then of being above L2, knowing that you were above L1, etc. And you estimate each of these probabilities by the same quantity, namely 1 minus 1 over n, hence this very simple formula for our estimator. And this is, in the following, what we will be interested in, hat p equal to 1 minus 1 over n to the n. Okay, the following slide just shows you through box plots the accuracy of the method when n, the number of particle ranges from n equal to 100 to n equal to 5,000, and for each box plot there were 100 realizations of the algorithm. Okay, and we can compare it because it's a very simple framework to the true value that we can get through a link with Fisher with Fisher contrails. Okay. So now the theory. The only assumption we need is to suppose that f is the cumulative distribution function of y is continuous, and then we denote lambda, the cumulative hazard function. This is a common tool, in fact, in survival analysis and reliability theory. We just have to recall that lambda is positive, is an increasing function. If you take lambda of q, then you get minus log of p. And most of all, thanks to assumption h, we know that if we consider f of y, this is a random variable, and this random variable is just a uniform variable. But if you take lambda of y, you get an exponential variable with parameter 1. Why is it interesting here? Because remember that L1 was the minimum of the scores. So if you consider the lambda scores, then since lambda is increasing, lambda of L1 is the minimum of n random variables with the same distribution, which is an exponential 1. And we all know that this is an exponential variable with parameter n. Okay? And then you can iterate this reasoning, and you can prove that the successive lambda of L1 and lambda of L2, etc., can be seen as the arrival time of a Poisson process with weight n. Okay? That's what this formula says. And this is very useful because we know everything, a lot of things about this arrival time of Poisson process. Okay, in particular, remember that the only random thing in our estimator hat p is the number of steps, but the number of steps m is the last index such that Lm is less than q. So put lambda on both sides. Lambda of Lm must be less than lambda of q, but lambda of q is minus log p, and lambda of Lm is the time of the arrival of the event number m. And this tells you that m is the number of arrivals for a Poisson process with intensity n until time minus log p. And we all know that from the theory of Poisson process, we know that m has a distribution, as a Poisson distribution with parameter minus n log p. Okay, and then we can deduce immediately the distribution of hat p. And in particular, we can compute the moments of hat p. It's very easy to see that hat p is unbiased. And more interesting is the variance of hat p. And here we have computed the relative variance. This is this formula. And this is a good approximation up to the order 1 over n. You can compare it to Monte Carlo, and you see that for the same precision, we just need minus p log p less particles with our method. Okay. But in fact, our method has a larger complexity. So to be completely fair, we should compare efficiencies of the algorithms. Efficiency is variance time complexity, and we can prove that in fact our method is more interesting than like classical Monte Carlo when the event the probability of the event is less than 10 minus 4. Okay, at least in this example. It means it's interesting for rare events, but not rare. Okay. Another remark is that this, in fact, this minus log p over n, this relative variance, is the best you can do with multi-level splitting, in fact. At least approximating, asymptotically. Okay. So we can also get confidence intervals for our for p, because we have said that m has a Poisson distribution, but the parameter of the Poisson is minus n log p, which is huge. Okay, so you can very precisely approximate it with a Gaussian distribution, and then you can deduce a confidence interval for p. What we can notice here is that this confidence intervals is not symmetric around p, but there is no surprise in this story because hat p is, since m is normal, hat p is log normal. And we know that log normal distribution don't have a symmetric distribution around their mean. Okay. So now I have to come back on a practical concern for the algorithm, because I have said at step 1, we kill the red cross and we want to replace it with a blue cross x star, which has the law of x, knowing that the score of this particle must be larger than L1. Okay, we call this law mu1. Yeah. So x star must have mu1 as distribution and must be also independent of the n-1 other particles. If we just had to satisfy the first point, then we could just clone one of the existing particles, for example, here. this one. Oh, doesn't work. Okay, this one. But in this case, this assumption, of course, would not be satisfied. So we need another tool. And this tool is very classical in Bayesian statistics and Markov chain Monte Carlo method. And it's a transition kernel K. We ask this transition kernel K to be reversible symmetric for the law of X. Okay? For example, in our for a Gaussian distribution, starting from X, you obtain X prime by adding an independent Gaussian noise with variance sigma squares. You normalize the whole thing, and that makes a job for any sigma. Okay? If you don't have an obvious sigma, an obvious kernel, then you can use Metropolis Hastings algorithms. That's what Bayesian statisticians always do. But in fact, at step 1, we don't use exactly K. We use a truncated version of K, which we call K1. Because so this formula is not completely is not rigorous from mathematical point of view, but it just says, okay, if you want to propose a transition for at the first step, starting from X, propose X prime thanks to K, and if the score of X prime is above L1, this transition is accepted. Else it's rejected and you stay at the same place. Okay? So our idea, since K1 has mu1 as this stationary distribution, our method is to iterate K1 a huge number of times, and then we will forget the initial condition. Okay. Last remark is about the tuning parameter sigma, which intervenes here, because you can see that if sigma is too large, then here the transition you have a large step, and when the algorithm go further, then the region is always smaller, and most proposition will be refused. Okay, so sigma shouldn't be too large, but on contrary, if sigma is too small, then okay, most transition will be accepted, but the particles then move really slowly, and so you will need a lot of time to forget the initial condition. Now I illustrate what we do with a few slides. Okay, so starting from I kill this particle, I clone this one, and then I want to stay with the good law, the law of X, knowing with mu1, in fact, the law of X, knowing that I'm not in this region. But I want to forget my initial condition. So I iterate kernel K1. This step, so K proposes this transition, and this transition is accepted because we are not in the bad region. And then I iterate, but this time this transition is not good. So I refuse it, I stay at the same place, I iterate, etc. In our simulation, we have iterated this kernel transition 20 times, and it gives the result I showed you a few slides ago. Okay. So we can also, with this algorithm, we can also tackle the reverse problem. The reverse problem is given a very low probability P. You want to estimate quantile Q such that the probability that Y is above Q is equal to P. So just take the same algorithm, but stop it after a deterministic number of steps this time. This deterministic is given by this ratio of logarithms, and this ratio of logarithm is approximately equal to minus n log p. Okay, and so thanks to the base formula reasoning that I made for hat p, you have the natural estimator hat q equal to lm. Okay, then with the assumption that the density of y at point q is not 0, we can prove central limit type result. And we get this asymptotic variance that we can compare to the asymptotic variance of the classical Monte Carlo estimator. Classical Monte Carlo estimator is simply draw an ID sample and then sort the scores of this sample, and then consider that Q is n times P largest score. Okay, and if we compare the asymptotic variances, we can see that we have the same improvement in asymptotic variance, which is that our method is minus P log P better than this one, than classical Monte Carlo. Okay, But there remains a problem, because if we want to construct confidence intervals for hat q, we can't use this formula, because you can see that here you have f of q. And f of q, you don't know it, and you don't want to estimate it, because q is already hard to estimate, but f of q is even harder. Okay. Anyway, once again, we use the Poisson trick, because the probability that q, so which is deterministic, is between two successive levels, is exactly equal to the probability that a Poisson variable with parameter m takes the value k. So what you are looking for is the shortest interval such that which contains 95% of the probability. And okay, you can just do, since n is large, you can just do a normal approximation, and this is very easy to derive. Okay, so you have these two indexes, and then you just have to compute these two levels. The difference with before is that this time you have to make additional steps, because m max is greater than m, so you have to let your algorithm go a little bit further in time, approximately 2 times minus a log p supplementary steps. Okay, and then the last slide is just an illustration of this confidence intervals for n equal to 100 particles. Okay, I'm done. Thank you.
I have a question. You have assumption that f is continuous, and you say you assume it's uniform.
The assumption that f is continuous, yes.
Yeah. Did you say you have to assume to be uniform? Maybe I didn't get it right.
Uniform on? Yes. Yeah. I have to suppose that f is continuous everywhere, because this is because I use the properties that when f is continuous, f of y. F of y is uniform, and it's the same way lambda of y is exponential. So I have to use it everywhere.
All right. Thanks, Steve.